You're a little bit better.
Okay, what about now?
That's getting better all the time.
We can try another one and see if it works better.
I think I can hear you okay. Let's see how it works if we need to improve things.
Okay, sounds good. Are we good to start?
We are good to go.
Okay, so we are Team 66 with New Mexico State University. My name is Ariana Yanez, and I'm going to be the team's lead engineer. So to start for our video review, uh, first off, sorry. We did have a test launch on April 27th. So before we get into anything, we want to talk a little bit about that. So our rocket is 148 inches or 12.3 feet. Our weight with no motors is 50.6 pounds. With the motor, it is going to be 77 pounds. Our CG is currently locked in at 92.25 inches with our CP at 109 inches, leaving us with a stability margin of 2.81. The motor that we are using is Aerotech, the N2220, the DM. One thing that I do want to mention for the test launch specs, our max velocity that we hit was 885 feet per second. With our fin flutter calculator, we figured that we wouldn't hit fin flutter until we reached 4,250 feet per second. So we're pretty safe there. With our motor, we do have an average thrust of 2,199 newtons. And with that in mind, as well as our weight, we have a lift to thrust weight ratio of 6.41. One thing that we do want to note is that at the test launch, we did have a wind speed of 18 miles per hour when we launched. So that did lead us to weathercock because of the strong winds. Our initial takeoff was really stable, so it has nothing to do with our CP or CG and our understandings. And then as well as the fin flutter, we would never even hit the max speed. So we're gonna leave that with the weathercocking due to the thrust to weight ratio, just because in order to have less weathercock, we want to have a higher thrust to weight ratio. So one thing that we're gonna do based off these findings is we're gonna work on losing a lot of weight. So that way we can at least hopefully get our thrust to weight ratio up to like 8 or 10, which means that if there was wind speeds at the test launch at around 10 meters per second, we would really mitigate the weathercock, making sure that we have a successful launch. Another thing that did happen is
Just before you go further, just going back to the earlier slide. Uh, so the numbers here, as far as your weights, how did they compare with what you originally predicted in your report number two? Uh, I'm assuming you're probably heavier than you predicted. That's
yeah,
typical.
yeah, from my
How much heavier are you? And again, how did these numbers compare with your predictions?
from report number two, we did gain about 7 pounds. And I think this just comes from, especially when we're loading up the recovery system with we use plumber's putty to make sure that everything is sealed and contained. And then as far as measuring the actual attachment points, those did add some weight. So I'd say we're about 5, 6 pounds heavier.
Okay, what about your basic flight parameters as far as velocities and stuff there? How did you compare?
Since we did get heavier, our takeoff velocity went from, I believe, 90 to about 84 feet per second. We're still above the 50 feet per second, but hopefully when we do lose some weight, we can get closer to that 100 feet per second.
Okay, I am curious, and hopefully you'll go into it. You say you want to move the thrust to weight ratio up over 8 to 1, which is going to be a pretty significant weight reduction. So I'd like to talk about that a little bit. How are you going to pull that much weight out of the rocket?
We did, I would say, over-engineer our body tubes. So we haven't really done a complete sanding of the actual body, as well as our subsystems. I think we went really safe. We did a high safety factor to make sure that everything was attached. But after test launch and seeing that nothing really broke and seeing that we don't need as much emphasis on that, we might cut some weight from the system themselves. And then when we go through the actual rocket, you can kind of see that.
Okay, all right, let's go ahead then.
Like I mentioned, the one thing that did happen is the drogue chute did deploy. It just did not deploy properly, just because of the weathercock. This altimeters and CO2 canisters did initiate the section separating the shiplings broke, but because that it was traveling at a higher velocity than it's supposed to. It did cause some shroud lines to shred. It did stay connected, meaning that we did have a safe recovery. But we are going to purchase another one. And then as far as we do have air brakes on our rocket, they had a malfunction. It was not flight critical. The switch was just not secured properly, so we weren't able to get them to start. And then we did have a payload no-go, which again is not flight critical. It's just the system is not ready to go.
Okay, when you say a no-go, was it on board for the flight or was it just not on board?
No, all systems were on board. They just did not actually.
Okay.
And then moving on.
So the proposal spec for this year, as we said, we're using an Aerotech N2220 DM, so dark matter. Empty motor case structure for the rocket's 50.6 pounds. The propellant weight itself is 26.4 pounds. Brings us to around 77 pounds when we're on the pad. Average thrust for this motor is 2,199 newtons. Maximum thrust is 4,472. Total impulse 10,657. It's a pretty powerful motor. Burn time of 5.4 seconds. As you mentioned, thrust to weight ratio of 6.4 to 1. And the launch route departure velocity is 87 feet per second, which falls short of the 100 feet benchmark, but it has been proven to be safe with the test launch findings. And the max acceleration that we'll be going under is 9.4 Gs.
Okay, I'm good with this.
And then the rocket structure, as you have here, which you'll see in detail more. We have our nose cone with our payload sitting inside, and we have our avionics bay, main parachute. Main parachute gets attached to the avionics bay, and then we have a recovery coupler, drogue parachute, our air brakes, and our prop section.
Okay, so your avionics sit forward of all of your parachutes. Or is there an eBay? Okay, so you have the eBay in between the main and the drogue.
Yes, sir.
Okay, so what avionics are actually up in the avionics bay?
Avionics bay.
So the electronics, we have the GPS. We also have a suite of sensors for orientation. In addition, we have our competition GPS. So that's the one that Ezra uses to actually track the rocket. And we do have an antenna so that we can track our own data that's coming live with avionics.
Okay.
And that's just a quick rundown of all of the electronics and the avionics.
I'm going to try to kick up the volume a little bit here. Let me look to see on because it's you're kind of quiet.
All right. So just to repeat that, can you hear me good now?
I heard you before, so it's just make it a little bit easier if I can kick the volume up.
Gotcha.
Let's see. All right, it's not obvious here where I can get any more volume. So yeah, if you can kick things up a little bit, that'd be great.
All right. Can you hear me now?
Yeah, I can hear you. Like I say, you're just a little faint.
Gotcha. All right. So next.
Tell you what, give me one moment. I'm just going to see. I've never tried using a headphone on this computer. Let me just see if I've got a headphone jack on here, and I'm going to try doing that. Okay, let's try this. Okay, is anyone speaking?
Yeah, okay, so can you hear us better?
Oh, more better, by far.
I'm glad.
Okay, I heard what you said previously, so let's just press on.
Okay, so moving on, we're going to go ahead and delve through the subsystems just on the PowerPoint and then whenever you see them in real life. So starting with recovery.
Alrighty, awesome. So as we said, our drogue chute is a 36-inch drogue chute. The deployment is at apogee. The descent rate is 65.19 feet, which meets section 6.3 of the drogue chute, the descent rate. We use 2 CO2 canisters. We have a 45 grain for the main and a 60 grain for the redundant. This is just to ensure that it does pop properly.
You said, is it grain or gram?
Gram, sorry. And then We have a main chute of 120 inch. The deployment is at 1,500 feet. And the descent rate for that one is 18.09 feet. Same as the drogue, 2 CO2 canisters, a 45 for the main and a 60 for the redundant.
Okay. And I'm assuming that's a shot from your deployment tests over in the corner there.
Yes, sir. We also have a video of it.
Okay.
And this was the 45 gram. This was one of many tests that we conducted.
Okay.
And then moving on, we will start talking about air brakes.
All right, so for our air brake system, we have 3 custom machine brake fins that are deployed linearly with the servo motor connected to 3 connecting rods, and the brake fins are connected to guide rails that translate the rotational motion of the servo motor into a linear motion. Our air brake system uses a high G accelerometer. It takes data every 1/100th of a second, and it's powered by custom lithium iron lithium iron phosphate battery.
Is the battery compliant with the D-tag?
Yes, yes, it is.
Okay. Well, are we going to be able to see that as we go through the rocket?
Yeah, you'll be able to see all those components.
Okay. Very good. Okay. Keep on your trucking.
Back to avionics over here. So we have the tele GPS, that is our competition GPS. It's on the 70 centimeter or 433 megahertz range. And so it does have APRS. And so that's so Ezra can actually track it in addition to us tracking it. I am licensed, so I have the technician's license, my call sign and everything. We also have on the avionics board the Adafruit Ultimate GPS, and so that's going to help us track it. So it's another redundancy so that we make sure we always have connection with the rocket. That one operates on 900 megahertz, and so that's amateur and it doesn't need a ham radio license. Like I mentioned, that one was the 33 centimeter, and we communicate with the payload via the ESP32s. That's the one actually sending the signal. You're going to see the big antenna right there. So let's see that it's connected to the Zigbee.
Yep.
Some of the sensors we have are accelerometer. We use that to detect whenever we launch, just so that we can have some data there. In addition, we do have a SD card on there where we're logging temperature, pressure, and some other data.
So it looks like you've got the black motherboard beneath everything here. Is that correct? Is that that has your interconnects between the various boards?
Yes, that is correct. It is our printed circuit board there, and that connects everything. And another thing to mention, we do have a what's called a latching relay. Basically, that allows us to give power to part of the board. And then once we actually activate the electronics, the whole board gets power. And that's just to save on battery and make sure we have runtime for the entirety.
Okay.
To mention, we do use the lithium ion 18650 batteries as well. And those are fine.
Okay. So one question there, all the different daughter boards that you have on there, are they connected and supported only by their connectors?
Yes. So essentially, if you can see the wires there, we do plug in the battery to one of the terminals, and essentially that powers the whole system.
Okay, but as far as communication between the various boards on here, they are okay. You've got traces on the motherboard. The daughter boards, are they supported on the motherboard only by their connectors?
Yes, only by the printed circuit board. They're only connected by those connections.
Okay, I'm not going to complain about it as far as an official, a quote unquote official complaint, but generally it's bad practice to rely just on connectors for structural integrity. Better practice would be is to actually use the connectors only for electrical connection. And mechanically support the daughter boards. Again, these are not the flight critical avionics. Well, GPS is, but it's working. You've flown it, so it's a suggestion. It's not a complaint or an issue. Any questions on what I'm saying there?
Um, sure. So actually, we can go back. Okay. So just to clarify, by the connectors, are you mentioning the wires there? Are you mentioning the actual printed circuit board as the only connections? Is that
Right. You've got connection between the various modules on the motherboard. So you're just plugging your daughter boards into the connectors on the motherboard, if I understand your design correctly. And that connector is the only thing supporting the daughter boards on the motherboard.
yes, that's correct.
Okay. So better practice is to use electrical connectors strictly for electrical connections and to mechanically support all the daughter boards independent of the electrical connectors.
Okay, gotcha.
And again, that's an observation. It's not going to go any further than this video. You are fine to proceed in this area for flight.
So for the manufacturing, our whole airframe has an outer diameter of about 6 inches, and this is due to the acrylic mold that we have, which has an outer diameter of about 5.75 inches, plus the mylar sheet that we put on it, and then the 3.5 yards of milk, of rolled fiber, comes out to about 6 inches. We use fiberglass and carbon fiber for our whole components. You'll be able to see them in a minute once we go down to our rocket. So we have a total of 3 fins, and they're all slotted onto the prop tube. They're 120 degrees space, and each fin has 16 layers of fiber with epoxy resin. We also have fillets both inside and outside the prop section, and we did a tip to tip to ensure that the fins were stable and they're being ventilated. Now for the couplers, we do have an airframe dome connectors, which you will be seeing here in a moment as we go down the rocket. And then for the recovery system, we do have a 1-inch band that's going to serve as a mounting point between the halo tube and the drogue tube. And then the airbag system itself should be secure in there with the couplers.
Okay.
So the payload is, well, it's actually located right here. I think you can see on the camera, but that image that you're seeing right there is actually from the test flight. It does have an electronic encasement that holds all of the electronics. It also held the battery. The current design that we have right now does not have that entire backing on it because we're trying to reduce weight. So we actually found a different way to mount the batteries, which you might be able to see in the animation, but you also might not. We did remove a lot of that material. Everything is 3D printed. We're going to try to get some things machined, but like I said, we are a little heavy. So we negated that and we just kind of designed it to where it would survive multiple forces while just being 3D printed. When you see that one, it's actually 100% infill right there, so it was a little heavier and it was actually too strong. It didn't even deform at all, and the drone was unaffected from the entire test flight, which, if I didn't explain what the payload was to begin with, it's actually a mechanism that actuates a drone out after landing. There are shear pins still, so it is required to break the shear pins. Like I said, everything is mounted onto it. The CubeSat is the only thing that's machined, which you'll see right now. In the test flight, we didn't use the machine one. It is also mounted to the electronic encasement right there, the blue one. And then that is mounted to the nose cone through some no-head screws and a bulk plate. The bulk plate is also reinforced so that it won't crack, because we did have some cracking in the past. And like I said, when you see the test flight one, there was no damage done to any of the systems there before actually running. We didn't get to run the system because we didn't have all the electronics and stuff ready for that. But yeah, those are the main components of the
So is there a video I should have seen here, or because you mentioned animation and all I've seen is the step?
There's an animation.
Okay, so you're gonna do that now.
Yeah, so it actuates outward, and it's just a motor that's twisting the lead screw. and then it has a little nut on there that connects to the actual piston there. That little flange piston, you can see it connects to the bulk plate, and then the bulk plate is of course mounted onto the nose cone. As for the actual drone itself, it's only secured by some little springs, which you can't necessarily see them too clearly, but there are some little suspension springs there that keep it in place, as well as the little arm that sits on top of it. But during flight, since it's sitting inside the CubeSat, we're not really worried about it jostling around because it is pretty secure inside of the CubeSat. And that's why we weren't too worried about taking any damage during the test flight. The only time where it is less secure is whenever it's actually actuated out, but by then it would have landed. So there's not too much worry there. And then when it orients itself, the springs as well as the little arm there are strong enough to support that weight, which we've done a couple times, just letting it orient itself in different directions.
Okay, so just a couple questions just to confirm. There are no pyrotechnics in the system for your payload?
There's no pyrotechnics whatsoever. It's all mechanical.
Okay, and the RF is basically just for radio control of the drone?
Yes.
Okay, and what, go ahead.
We actually connect through avionics. So avionics runs our system. And then once we get there, we're going to fly it manually because we couldn't do the autonomous anyway because they didn't let us. So
right.
Doing manual, we're going to be out there and we'll be able to just connect ourselves. There's a little radio that connects to the computer that we take out there, and it just signals directly to the drone. It's for the Crazy Fly client, which is the drone that we're using.
Okay, so all of the RF functions are basically on the ground, and the flight of the drone is manually initiated on the ground.
Yes.
Okay, I'm fine with that.
So that's all we have as far as the PowerPoint. So we can now start going through the entire rocket. So we actually did a entire assembly just so we can see how every section fits together. So we'll go ahead and start with that. Starting from the nose cone, we'll go down, and then we'll start from the propulsion section and go back up, taking out every system.
Okay, that's good.
Sounds good.
Start taking it out?
No, I'm just gonna see.
Okay, so all I'm seeing right now is your small inset photo. Can you remove the PowerPoint so we can get a bigger picture of, there we go. Okay, looking good.
So we're gonna go ahead and start from the top. So as you can see here, we do have our nose cone, like our manufacturing lead mentioned, is made out of fiberglass. Directly sitting right underneath it would be the payload section that is going to be held on with 3 M4 shear pins that the mechanical system will break. Moving on is the avionics section. Both the payload and the avionics sections are held in with 1032 screws. And then after the avionics section, sorry, I catch up. After the avionics section right here, we do have the main parachute and those connections within here. Within here, right here is the first coupler, which is the airframe joint thing. This is going to house the E-bay with all of the CO2 systems. There is a U-bolt attachment on the avionics bay that you can go ahead and see, and another one on the actual E-bay itself for the parachute shock cords. And then
just a quick, before you go back further aft, just as a quick question, looks like you're using rotary switches on the eBay for your electronics. Where are the switches or what for energizing or arming your avionics bay? I didn't see those.
Oh, so for the avionics bay, actually, you could jump over here really quick. Switch over here, and we can do this from a distance we've tested. It works very consistently up to 2 miles. Beyond that, we sometimes have to wait just a couple seconds, but it's usually pretty good. But you're going to see the switch here, and basically this will just give full power to the board.
Okay, so you're basically RF energized for your avionics.
So we are not connected to energetics at all. For the avionics, we're not connected to energetics. This is simply for our logging the data and getting all of that flowing.
Okay, but all I'm saying is you're switching there is it's all RF. There is no mechanical switching on the rocket.
No, it's all RF. That is correct.
Okay. The only essential system that's up there is your GPS, from what I saw, because that is flight essential. Is
Sorry,
that
could
a
you repeat
correct?
that?
Could you repeat
My
that?
my statement is that the only flight essential electronics up in the avionics section are your GPS receivers and transmitters.
That is correct.
Okay. All right, keep on going. We're back at the eBay. Interrupt you on the switches there.
Thank you. So then with the A-Bay, we do have 4 shear pins on each side. It is 6 inches on this side, 6 inches on this side, which meets the 1 caliber standard in the DTEG. Moving down is our drogue tube, which houses the drogue parachute. Again, we do have the attachment points for the shock cords. Lastly, we have our air brake system, which sits right here. It is housed in a coupler, and instead of using a band like you can see on the eBay, the actual band is the system itself. So right now it is PLA. We did get it machined, so you can see 1/2 in there already. We are working on putting it together, but we ran out of time. So we're half and half, but the system has flown before, has worked, and has gone multiple test flights. And then moving down, we have our 1515 row buttons. We do have 2 of them, our prop section, and then we have our fins, which do have the tip to tip. So fin flutters really non-existent. And then over here, we do have our motor retainer. So we did do a epoxy fill. We did have the bolted in kind of retainer. So we bolted it in first, and then we did an epoxy fill inside. So it's super secure.
Okay. What kind of epoxies did you use for bonding?
We used a 2:1 epoxy resin ratio, and then we did throw in some milled fiberglass to have it like a snot.
Okay. What brand of epoxies though? West or JB Weld or?
US Composites.
Okay.
And then so that's the rocket in its entirety. And then if we take it apart, we can see every subsystem inside.
Okay. All right.
So we're gonna go ahead and start with the prop section.
Okay. Is the motor case installed right now?
No, it is not.
Okay. And this is the rocket that has flown, correct?
Correct.
Okay. You mentioned that there were some issues with the drogue on the first flight. Was there any airframe damage that required repair?
Yes, there was on the drogue tube.
Okay, so when we get there, I'd like you to point out what repairs were made there.
Sounds good. Yeah, so first we're gonna start with the prop section. As you mentioned earlier, we did have a tip to tip on the fins, and I'm gonna go really quickly over how the prop section was built. So first we have the propulsion tube, which is the bigger outside tube, and then we also made a motor mount tube, which is where the motor casing is gonna go. So now the way we mounted the motor mount tube inside is we had centering rings. So we have a total of 4 centering rings. If you look closely, we would have one right before the fin, one right after, which is spaced 13 inches apart because that's the root core length. And then after that, we had a spacing of 7 inches between each centering ring. So with those centering rings, first we tacked them onto the motor mount tube, and then we also tacked on the fins with a fin alignment jig that we have. After that, we made sure to put fillets on both the centering rings and the fins inside of the motor mount tube to make sure it's really secure. After that, we had to slot the prop tube. So we slotted it. We slid the whole motor mount with the centering rings and fins across. And then after that, we made sure to also put fillets on the outside. So we have internal and external fillets. So now that was done, all we had to do was repair these sections where the slots were at. And then finally, we did some sanding of the snot and the carbon fiber, and then we did a tip to tip on all the fins. So we used the same, we used plain weave carbon fiber for the tip to tip, and then we also used a 2:1 ratio of the resin to hardener with the curing time of 24 hours. So once those 3 tip to tips were done, all we had to do was put on the motor retention system. So as our lead said earlier, we have to screw it in first, and then we put a full epoxy with milled fiberglass to make sure it's really secure, and that is essentially the whole propulsion system.
Looks solid. So one question you didn't cover there is how are your your rail buttons attached to the rocket?
So the lower rail buttons attach into the centering ring. We actually drill into the centering ring and then helicoil it in. So that one's attached through there. The top one is attached since there's nothing much up here with the nut on the inside of the bolt.
Okay, and there's nothing on the inside for the top that's going to catch on any recovery components or anything on the inside. I'm not sure if I get. Okay. All right, very good. Thank you.
Okay, so moving on, we're actually gonna remove the bottom half of the prop section. Yes.
Okay, and there's normally shear pins installed here, correct?
Yeah, so
Or
we
not?
actually have our air brakes coupler here. So this part of the propulsion section actually is not supposed to come off during flight.
Okay, all right, very good.
We have our air brakes section here, so you can see right here is actually the coupler that houses the air brakes, with the other 6 inches going in on this side. And then the top of the air brake section is actually where the U-bolt is for the drogue parachute. So
Okay.
your pins are actually only going to be on this side of the rocket.
Okay, so one thing going, so just going, if you could, I want to see more of that forward bulkhead there. So are there any washers for the U-bolt on the backside to help distribute the stress at all?
On the back side of that bulkhead, there is a plate that has 2 holes cut into it. So that's capturing them together along with nuts, and they're also epoxied on there.
Okay. What I was looking at is there anything just to help distribute the stress? It sounds like you got that plate back there to help distribute stress on the bulkhead.
It has that backing plate, yes, sir.
Okay. So where we're looking right now, um, there are this has shear pins up here, correct?
Yes, this side
And this
is
this
going to be
joint.
the shear pin side.
Okay, what kind of shear pins are you using?
Oh, actually, no, this is not the shear pin side. This one stays completely in. We're actually going to do the shear pins on the E-bit. So this ones are attached by the 1032 on both sides.
Okay, very good, very good.
And then we can go ahead and pull up the air brakes without pulling up the parachute. That's okay. Don't pull the parachute.
Or just disconnect.
Yeah.
Yeah, you can go ahead and disconnect it. Go ahead and do that. And if you want to put the booster section out of the way, that's fine too.
So, like I mentioned, the air brakes are housed in the coupler. This is air brakes on the left hand.
So how this works is we have all threads going through completely, and we have 2 fiberglass coupler sections. So basically the all threads are nice because we can put the air brakes under the right amount of compression, and we can add spacers in here to modulate how much pressure is actually on the fins when they're deploying, so that it's a good firm fit, but not so tight it jams up the servo. In the top section here, we have all of our electronics, and as you can see, right here, this is a threaded 1032 safety for the electronic system. So basically, the air brakes cannot be active until we screw 1032 all the way in here. It goes through two different bolts, which are put inside a plastic ring that's been epoxied onto the inside here. And once we screw that pin all the way in, we'll hear a 5-second calibration cycle with a beeper on it so that we know that it's achieved continuity. And during that 5 seconds, it'll collect acceleration data. Then after the 5 seconds, it's good to wait on the launch pad and listen for motor. And in this central section, obviously the servo motor, it rests along inside on the center line where the U-bolt is, and it actuates, it's facing down. And as it turns a servo horn adapter, which linearly actuates these on their dovetails. I don't know if you can hear me all right. I'm moving the microphone all around. Then
You clip it on your shirt.
Oh, that's so convenient. Okay. Well, if my shirt would pull up, right? Okay, and then the bottom section doesn't really have anything in it except for the all threads that go through to the bottom and connect to this fiberglass coupler.
Looks good. The only question I have was, I'm not sure how easy it is just to see the battery that's in there.
Oh, well, we would have to detach these 3 bolts.
So, yeah.
Brian's gonna be so mad at me, I might not actually be able to get it back together.
You're rich. Do you want, we can go through, like, the rest of the system.
Okay. I don't need to go into super detail on this. It's not a flight safety essential system, but because of the detail requirements, I just want to make sure that the batteries are want to see the battery and look at it.
No, I was gonna say we can go through the rest of the rocket, but he's going pretty fast, so I think we're okay.
We also have an identical battery, I think, over there in one of those tubs.
Yeah, if you've got, I mean, I was about to say, if you have a spare battery, you can just show me what the battery is. I'm good with that. Again, the system is, if it doesn't work, it doesn't affect the flight.
Yeah, that's actually it's 6. This isn't the exact one.
No, this is not. It was just one.
Oh, okay. I'm sure Brian stuck it in here because it won't work without it. So it's like some cons.
Yeah, yours are just mounted on there. You don't have to like. Just the same.
Okay, so that last battery you had was not the correct battery. The one you were
No,
holding.
Sir,
it looks similar, different kind.
we're almost there.
Yeah, hold on to that while you buy
Okay, I don't want anyone to end up in a wall or anything.
That's a lot of money.
Yours is usually a lot.
I was alone.
Okay.
Guy.
Okay, sorry about that, Steven. Almost there, almost there.
That's okay.
At
Just
least now
take
you
your
have an
time.
interesting
Take your time. I don't want you breaking anything. I don't know what your schedule is. I'm open ended.
No, we're okay. I know Daniel's got
You have to sell.
10 minutes to exam, so we're almost there.
It's because he's configuring these cells, I'm pretty sure.
Okay.
Yeah, because he had those cells yesterday. I don't know where he put them. Like you have the 18 whatever, 1816, 18650. 18650.
So this is the kind of battery that we'll be using in the future. So basically, how it works is,
Yeah.
that's okay. We're gonna have I don't know, answer everything. We're gonna have a Velcro strip attached to this. It'll attach to the top plate of this board where our control system for the air brakes is housed. Then it's gonna plug into this battery port down here, and we have this section, which is the continuity switch, which is going to be epoxied down by where the safety pin is going to go. And
Okay.
it will only be continuous when the screws. And there's a buzzer in there so that we know exactly.
Okay, so the battery sits on top of the Velcro that's in there. Is there any tie wraps or anything in addition to the Velcro?
Not for the battery, no.
Okay, is it just tight in there that it can't go anywhere? Is it only relying on the Velcro, or is it also constrained?
It's relying on the Velcro and also the wiring, and also the fact that the sled that we put this entire thing on is bolted into the all threads.
Okay, so it doesn't have very far to move, is where I'm getting at.
No. I kind of have to push it in there when we're installing it just to make sure.
Okay, all right, I'm okay with it. Like I said, part of it too is if it doesn't work, it's not a flight critical system. It's critical to your performance, but it's not a flight safety critical system.
We certainly hope it works.
All right. Okay, I'm good.
Thank you, Daniel. Okay, so moving on, we do have our drogue tube. So this is the one that is going to be mounted with the 1032s connecting to the air brake side, and then the shear pins, M4 shear pins. We do have 4 of them connecting to the eBay side.
Okay, so this is the first separation in flight.
Yes, sir. So you can see, Mont's going to go ahead and show, like you saw the parachute connection on the actual air brakes coupler, and then when we go ahead and pull that out, the parachute should just come right out. So this is the old drogue chute, I believe.
Okay, but in reality, though, it's coming. Okay, so just to make sure I've got this right. Okay, so the shear pins are behind us here or in front of us? I'm still.
The shear pins are going to be in front.
So you kind of actually deployed the drogue in reverse from what it
Yes,
normally
sorry, we
is.
just did it this way because we already had that section off.
Okay, all right,
But it's
that's
going to come
fine.
off on the other
So
side.
just let's go back to the. I just want to see. I want to see the parachute fall away. Just move the camera down to the parachute. Okay, so and just pick it up. I want to see it fall out. Basically, that everything is just to pick up the drogue line and just let it. Okay, that rubber band or whatever that was is not there for flight.
It's just to storage.
No, just for right now, it's just for packing and storage purposes.
Okay, so you having your checklist to make sure that none of that stuff is there, correct?
Yes, yes, sir.
All right, I'm good. I'm good.
You want to strap it or you're okay?
You're fine. Okay.
Perfect.
And what is that shock cord? It looks like nylon.
Yes.
Okay, and that's what about 5/8.
5/8.
5/8, yes.
Okay. All right, I'm good.
Okay, so moving on is the road tube. So where's the part that was- So
Okay,
this is the one that was we did have this tiny weird zipper. So this part was actually on the side, right? It was right here. So whenever the drogue chute came out at too high of a velocity, which it's not used to, the shroud lines did kind of rip, and through that, it did affect the tube. Before it was sitting at 24 inches long, we were able just to cut it off because it wasn't that big of a deal. We changed, now it's now sitting at 21.5 inches, and on all of our simulation software, this length change is not an issue, kind of help us out a lot. The parachute still fits inside, and it does help a little bit with the weight reduction, so that was a plus. So this side is the M4 screws, so we can go ahead and pull it off.
Is that the same shock cord that you used for the previous flight?
Yes.
Have you inspected the shock cord that when it came across the carbon fiber there, that there's no damage to the shock cord?
Yes, so we actually believe that it was actually the shroud lines that just kind of hit it out because they actually bundled into a ball, which kind of represents how this kind of was hit instead of the usual zipper down. It's more of a bulky, just tough hit.
Okay, and you said you're replacing the parachute from that flight?
Oh, is that
Okay, very good.
that's the new one.
Let me just look at the aft bulkhead there. Okay, so those are your CO2 canisters. I didn't see it there. You can just answer the question. Do you have a swivel on your drogue chute?
Yes, sir.
Okay. And what's on the back side of the U-bolt? Is there any kind of a plate or anything to distribute load on the bulkhead?
That one has the same metal backing as everything on the rocket that has U-bolt has the metal backing with epoxy.
Okay. Okay, keep on going.
Yeah. So the other side.
So now we're doing the main deployment.
Yes, sir. Would you like to see it pulled out?
Okay, so are we doing this in reverse? Is this where the shear pins are, or are the shear pins up towards the front?
This is the correct orientation. This is where the shear pins are.
Okay.
Because the image is flipped on there for some reason.
Okay, so just walk away from it. Let's just see how the main deploys.
So as you can see, you have connections.
And if you want to go handle it, I mean, you don't need to pull. If you just want to take it right where your hand was there and pull it from there instead of walking across the room, I'm fine with that.
And then it is housed in a parachute bag that is attached. So
Okay.
the lines would just come out, and the actual parachute itself is just gonna release.
Okay, looks very good. Looks very good.
And then the bag is still attached, which we can get into in a bit. So moving on, that's all that fills up this section right here. And then you do have the avionics. I thought you just threw two outside. So we're gonna go ahead and pull out the avionics section.
Okay.
So,
And while you're doing that too, I would like to look at your eBay inside that too. If someone needs to work on that while you're
Okay.
working on avionics.
We'll go ahead and pull that out and I'm gonna just. So before we pull it out, you can see the swiveling connection on the U-bolt. Like we mentioned again, everything is gonna have that metal plate backing with the epoxy. For the actual avionics system itself, since it is taking so much force, we actually implemented these aluminum rings, and this is where the 1032 screws will actually go into from the outside of the body tube into the ring and then house the system.
Okay, so one thing going up forward there, the battery. I want to see the battery install. Okay, is that the flight installation? Are there any tie wraps or anything to hold the
So,
battery in place?
During flight, we'll have the zip ties if you flip it around. So for the competition GPS, we are using a separate battery just so that we keep the same voltage, so we have consistent data coming in. But it'll be zip tied just like this, the front one here, in addition to the Velcro, which is still pretty secure.
Okay. All right, so there's no restraint fore and aft on that, other than the Velcro.
So it'll be Velcro in addition to the zip ties.
Okay, but I said the only restraint fore and aft from acceleration is the Velcro.
Oh, yes.
Okay. All right, I'm good with it. I'm good with it. Preference would be is to have a tie wrap fore and aft, but the fact that you've got the Velcro there and you're holding it down side to side with the tie wraps, I can live with that. You're good where you are.
So then moving on, the payload tube is now completely empty because we did separate the actual payload from the cone. So the payload sits inside the nose cone, and then you can see here, this is the 1032 attachments on the payload main body tube.
Okay.
There's a few of them.
Okay. You don't need to actuate the payload and the like for this because I'm happy with what I saw on the animation earlier. And again, there's no pyrotechnics or anything up there. So unless you really want to, I do not need to see the payload operation.
Okay, yeah,
That will all be on the
have it
ground.
wired up, so. But yeah, oh, so yeah, it just has the four connection points which go along each one of these. And that's just where it's mounted. And then as for this one, you can kind of see where the I don't know if you can see it. There's the bulk plate in there. And the
Right.
bulk plate is mounted with these just no head screws. Same thing. This one only has 3 connection points, but we've tested a few times, and the only thing that would ever fail was actually the bulk plate, and that's why they're reinforced with those nuts and bolts and stuff like that. And besides that,
What?
it just has
Okay.
the
What
three
kind of
the 3 shear pins that connect right here, and that's what actually connects it to the rocket during flight. And then those will be broken off through the actuation. As for the drone itself, like I said, when you look at the test flight, there was no damage or anything, but it's pretty secure in here, and it'll actuate whenever the screw actually runs and stuff like that.
Okay. Your batteries, what kind of batteries are the drone is the
We're
drone
using
using?
the lithium ion, the 18650, and they're
Okay.
the cylindrical cells, and they're mounted with they have their own casings to be mounted.
Okay. What actually, and that looks pretty big for that drone. Is that the battery for the drone also?
No, the battery for the drone actually is in the drone, and it's actually it's turned on just from a little pull tab that we have that breaks the
Okay.
circuit.
What kind of battery is it?
I'm gonna see if I can pull it out for you.
Yeah, like I said, I'm not, is it a, what I'll call a pillow pack battery or?
Yeah, it's just a little 3.7 volt guy.
Hold on, hold it.
All right, I'm okay with that. It's a smaller one. I'm not sure the battery is totally compliant with the D-Tag, but I'm okay with it.
It's from the manufacturer, so
All right, if it is, then I'm good. Okay, I'm good with the payload stuff.
Awesome. So the last thing is again the eBay. So we're ready for it.
So you see it pretty well from there.
I can see it fine. So the front and back ends look the same, basically.
Yes, sir. So on each side of them, you have the Raptor CO2. This is where the canisters go into, or where it comes out from, sorry, and the terminal blocks, so that we can put the fire wires into these. And I'll go ahead and start folding it apart.
Can I see the back side of that bulkhead when you take it out, when you take this out? Okay. So you said the metal plate there. I don't see for the back side there. You said there was a metal plate that on the back side of the U-bolts.
Yeah, I think I confused them. These ones only have the nuts, but they do hold the stress pretty evenly.
Okay, how thick is that bulkhead?
The bulkhead,
Is that like quarter inch or 3/8 based on
uh,
the?
they're each about a quarter inch, but there's two of them stacked together.
Okay, so it's by half inch total.
About yes, sir.
Okay, I'm good with that.
Just take these off. Like I said, these are the wires that run to the terminal blocks, which actually connect to the altimeters. So
Okay.
they're pretty good size and length. Terminal blocks inside and outside are epoxy down so that it does not come loose during flight.
Okay. Actually, just as a point, and again, you're fine for flight there. It works, but generally, it's bad practice if you have excess, not to have excess wire on board. Better practice is just cut the wires to the length that you need. You need your service loops, but it's not good practice to bundle unused wire.
No, yeah, yes, sir. These are just ran a little bit longer just because when you're loading the eBay, you need to pull it out from one side. You want this one to reach all the way.
Okay, so if you need service loops, that's fine.
And then we have the sled. So the sled is only contains the altimeter with its battery pack. Like I said, the altimeter has slots for both main and drogue, and you'll see right now where the switch connects to.
Okay, that looks good. You've been doing pull tests where you go into terminal blocks?
Yes, sir.
Okay.
And then battery packs are held on with both Velcro and zip ties.
Do
Altimeter.
you have any? Okay, you don't have any zip ties fore and aft. You're just holding it down to the Velcro with the tie wrap, basically.
The zip ties go through the sled. So
Right, but the only thing that's restraining the batteries fore and aft is the Velcro.
yes, sir.
Um, okay. Let me see end on view of that there. I just want to just turn it 90 degrees. So the battery, rotate it flat. Not there we go. Okay. So I can live with it. Just for the future, I really would like to see some kind of fore and aft retention other than the Velcro
All
in the
right.
future. I'm not going to write it up for this one. The other thing is the battery that's on top is much better secured. It doesn't have the big loops that the battery that's on the bottom right now. If you want to take a look at it for yourself, you've got a pretty good. So when you secure the battery, secure it like the one that's on the top, not the one on the bottom.
All right. Yes, sir.
Try to get those tire wraps as tight as you can.
Mhm.
Okay. And you got two RR. You got the two RRC3s, or
Yes, sir.
what's on the? Okay. Okay, it's a clean installation. That's good. All right. And your switches, how is that? How do your switches connect on there?
So the switches are on the inside like this. They run out, like I said, a little bit of wire play so that I have room to move it around, connect them. And the switches just go connected into the RRC3s themselves.
Okay. And again, make sure you don't have too much conductor exposed, and make sure you do excuse me, make sure you do your pull tests.
Yes, sir.
Okay, looks good. Anything else?
I think that's everything we have for today, unless you have any additional questions or if there's anything else that you'd like to say.
So a couple questions. One was I didn't hear them, which I didn't expect to. Is your flyer of record or
Yeah, our flyer
mentor on
record is
here?
actually our project manager, Juan Diaz.
Okay, all right, real good. So I'm just going to ask your group here. What keeps you awake at night about this rocket?
What keeps me awake? In terms of safety, nothing.
Okay, what about for success?
For success, we need to lose some weight, but I mean, I think that we're gonna be fine. We're gonna hit 10K. Our There are some manufacturing issues that we're running into right now in terms of the air brakes, but those are gonna work. They're gonna operate and they're gonna slow us down to get 10K. The only thing that keeps me up at night about my payload is getting it to run. There have been a lot of issues in testing, and so right now we're dealing with electronic issues where we're actually burning up the motor driver. It keeps overheating. And so we're currently fixing that. That's why one of our batteries is actually missing. So we had to order a new battery with strong voltage. And then there's just a lot of little intricacies that we forget sometimes whenever it comes to like the friction fit. Like right now, it's a little tighter on the nose cone, and that just gives me more force that I have to actuate. So,
Okay, so one other thing we didn't talk about here is checklists. What do you have for checklists?
Yeah, we have checklists. I am gonna submit them with the technical report, so that way they can be seen by the Hero X and Ezra. As for in person, we do have, trying to put it right here. We have a launchpad checklist. We have a pre-flight checklist for eBay and recovery. We have an abort and recovery checklist, as well as a pre-flight checklist for the propulsions.
Okay, so one of those, maybe your abort checklist. So you're on the launch pad and you're armed, you're ready to fly, and for some reason, be it weather or while you're getting ready to fly, you have a problem with the rocket, you're not getting the right beat pattern. Do you have a scrub checklist there to safe the rocket before you take it off the launch pad?
Yes, so we have a abort weather no-go checklist. With that, we also have to start, we have a misfire, so the motor does not fire checklist. We have a CATO checklist. We have a live CO2 after landing checklist, the abort weather no-go checklist, and finally a standard recovery checklist.
Okay, very good. Very good. Okay. This was a very professional review, a very thorough review. I want to commend the team. I'm going to submit basically, I have no issues for you to proceed for flight.
Awesome. Thank you so much, Stephen. We really appreciate it. And thank you for being our safety reviewer.
Okay, and good luck for your flying.
Thank you. Have a good rest of your day.
All right. Unfortunately, you're competing against one of the teams I'm a mentor for.
Ooh,
Because
who's that?
I'm the mentor for UTEP.
Oh, well, our Rockets
Don't
named
tell them
three-peat
secrets.
because we got to win the Chili Cup 3 times now.
Yep.
Oh,
So I will admit I have a vested interest here.
Yeah. Well, we'll see who wins.
Yep. All right. Well, good luck on your flying.
Thank you so much.
All right. Bye-bye now. I'm logging off.
UTIP just lost